Good afternoon, everybody. It's my pleasure to introduce Dino to Google. Dino's a fellow at Cisco Systems. He's been at Cisco since 1991. Has been building routers for 26 years. Been active in the IETF for 19 years, and you probably have seen his name on multiple RFCs published by the IETF and various standards. He was also a co-founder of Procket Networks that was bought by Cisco Systems, so it was a little bit of a detour for Dino around 1999. Of course, Dino has intimate knowledge of most routing protocols. He's particularly a specialist in multicast, most notably. Today he's going to talk to us about his latest protocol draft, Lisp. And just as a matter of housekeeping, this will be published externally to Google Video, so if you can hold your confidential questions at the end, and they'll just edit that off. So please join me in welcoming Dino to Google.
So we've been trying to fix routing in the internet, and this is a proposal that we're going to focus on called Lisp, and we believe it's a level of indirection that's going to possibly help things. I've gotten a lot of input from service providers and hosting vendors and content providers like yourselves, and we're hoping we're in the right direction. But this talk is not only going to benefit you, I hope, but it's going to benefit me by getting feedback. So it's a fairly technical talk, and you guys are actually the first ones that are seeing some of this content, especially the mapping service content down here. This is basically, does this thing work? Yeah, I just can't see it. So based on all those large numbers you gave, I'm getting old. That's why the numbers are large, right? But anyways, the mapping service is pretty new. New meaning it's just weeks old, and we almost are going to get it down in spec form in the coming weeks, trying to get it available for the IETF in July. So you guys are really the first public guys that are seeing this, so it's pretty fresh, and a lot of new ideas and a lot of ideas from previous protocols and architectures of the past. But we'll start off with a problem statement, look at the solution space with respect to only looking at Lisp as the solution. There's other solutions in this space called Shim6, HIP, and GSE, which we're not going to explore at all. We'll talk briefly about the categories or classes that they fit into, but we're going to just focus on Lisp because that's the work that I'm working on, or we're working on. The basic problem statement is we want to help sites, large content provider sites that are huge bandwidth sites, and internet service providers. We want to reduce OpEx and CapEx. I'm personally very worried that all kinds of vendors are pricing the internet too high, and we need to make it cheaper. So I'm looking at solutions that reduces protocols so it can reduce operational expenses and try to build cheaper systems. I work in the DC3 product area at Cisco, and we're trying to build a high-density, low-cost switch/router, and all the challenges that are associated of really making it low cost. So we're worried about CapEx as well as OpEx. We want to introduce some addressing flexibility. Hopefully a level of indirection could solve some of the problems that we're seeing in the internet. The solution may introduce some forms of mobility, but we're not totally sure if it's going to scale. There's a lot of large tables in a very small number of places in the network that would be needed, so it would be interesting to get your feedback. So we think the solution space is address splitting, and address splitting through a level of indirection, and I'll get into that in much more detail. And it's also been, so these are kind of all the cliches. This is known as a jack-up model. Okay, where you take the protocol stack as is, you jack it up, and you put stuff underneath it. And we're not talking about putting a layer 2 infrastructure underneath it like ATM or anything, or Sonnet or anything like that. It's another network architecture underneath it. And the Lisp solution is focusing on a network-based solution versus host-based solutions, and we'll talk more about that. And then I'll describe the data plane, and then what I call the Lisp control plane is the mapping service. Okay, so operationally what we want to do is we want to improve site multi-homing, and we want to improve ISP traffic engineering as well. We want it to be a little bit more flexible, not have to depend on MPLS, because there's solutions in IP that can work as well. So MPLS is not the only tool in the toolbox. We want to reduce or eliminate completely site renumbering. IP address renumbering we want to be able to eliminate if we can. And we want to reduce the size of the core routing tables at the same time so we could bring those lower cost forwarding chips to you, and then price per port goes down because of that. PI for all, PI here stands for provider independent addressing. So sites may, and we're seeing the registry starting to allocate PI blocks to customers, which means that the customers' addresses don't fit into the topology, so those addresses are completely unaggregatable. When they're unaggregatable, that means the internet will eventually be flat routing at the site level everywhere. Will that be able to scale? Does this make sense? So this is the nervousness that's happening and the urgency to put something in place to solve that. And mobility is going to be hot. We have some form of mobility that maybe a locator ID or a level of indirection can solve, and you guys could judge that. So architecturally, what we're going to do is, it's just one architectural concept that we're going to introduce here, and we're going to take the address and we're going to split it into an ID and a locator. And throughout this presentation, wherever you see green numbers or letters, it's referring to the ID. Wherever you see red letters, it's referring to locator addresses. And we'll explain how all that works. This effort was provoked at the Amsterdam IB routing workshop last October. And people said it's been 10 years and we haven't solved the routing architecture problem. We went from IPv4 to IPv6, but the only difference is a packet format change and an address length change. Nothing else is really different. So we really need to look at the routing architecture in the capital I internet as a whole. So these are some references on where you can look at the problem statements. I've been thinking about this problem for nearly 10 years now. And I'm ready to start working on a solution, so that's what's motivating me. So I started working on this last November, and so what you see is about a 6 to 9 month effort that's in place and continuing. So sites and ISPs cannot control ingress traffic paths. They can control which way they send packets out, and at their edges they can decide where to send it. But to be able to get packets in, it's the upstream guys that use BGP best path selection that decides which way to get to you. So you can't control which way packets come in. So since you can't control which way they come in, but you can't control which way they go out, you just basically have this wash sort of agreement with your peers. You say, if you send me too much stuff over here and I don't like it over here, I'm going to send you stuff over there which you don't like over there. So we want people to be able to control their egress as well as ingress paths. And that's both at the site level and at the ISP level. Okay? The only way people can do that today is by injecting more specific routes. If I want to be able to attract all these flows and I just send the one aggregate this way, they can only send it this way because they believe this path is not available. But if I say I want to punch a hole in that address space so I can get an exception of that block to come this way, I inject a more specific route. Well, injecting more specific routes into the internet is not a good thing because it grows routing table sizes. So we're finding that traffic engineering is affecting the size of the routing table, and we're losing the aggregatability of the network. And it requires large tables, lots of meshing, and we're having problems managing that. You get what you want. At the expense of everyone else, you inject a more specific route and you don't care, because what happens is you get the paths this way, but since you injected the more specific route, it continues to flow wherever it needs to flow in the internet, and everybody pays for your traffic engineering benefit, okay? And we suffer from routing table bloat. What is happening at the same time is the registries, as I mentioned, are giving out PI address blocks, and those PI address blocks are causing routing table bloat too. I don't want this presentation to say that the routing tables are getting too large, routers can't support them, therefore we need a solution. The amount of multi-homing that is increasing in the internet needs to be solved, and when we solve that, we will also make the routing table scale at the same time. So the IETF seems to want a big problem statement before they take a solution seriously. But I also want to give features while I'm solving problems at the same time. So I don't want that to be misunderstood. Sites like PI blocks for two reasons. It's the same reason why you like your cell phone number, and if you switch providers, you can keep the same number for the rest of your life. You don't want to have to change. You don't want to have to tell anybody about the new number. You don't have to renumber hosts inside your site. So if you get a new PI block, you renumber all your hosts and routers one time and you never have to do it again. That's the misled impression that a lot of sites are getting right now. Registries want to sell address blocks, so they're motivated to sell them. So why not? I don't care about the internet, it's somebody else's problem, right? PI blocks injected to the core gives you flat routing. Major routing table bloat again. Then mobility. Mobility is pretty hot, right? There's People are throwing down around hundreds of billions of dollars worth of revenue to solve mobility or to provide mobile solutions, not only in just handsets, but applications. I mean, you guys are very aware of this. So low latency and doing quick handoffs are very important as well. How do you do that when you're when you're at Google and you move to the Starbucks? Do you want to keep Google's address? Does it matter? Do you want to keep your sessions alive? All these sort of things are questions you ask for mobility. We think a level of indirection with a locator ID split can help this problem. The question is, can we make it scale? That's always the question. So the solution space is that let's stop overloading an IP address. That is the problem. It holds semantics for both identification and location. We need to have something that says, this is me, Dino, and right now I'm at Google, where this afternoon I'll be at Cisco, or I'll be at my house. Those latter three locations are things that are changing frequently, or can change frequently. In the case where you're changing from one ISP to another, that's a subscription time change. That changes less infrequently than me on a mobile handset, or me taking my laptop, closing it, and moving somewhere else and opening it up. Arguably, we've done that already, but when you move and you close, your ID and your locator changes at the same time, and you do lose your TCP connection. You do not lose your Google session, but you lose your TCP connection, right? So we need a decoupling for some flexibility, and the big question is, should this be solved at the routing layer? That's a question that deserves to be asked, or should you solve it at a session layer? And you guys have done some work on that where you solved it at a higher level. It remains to be seen if we can do that and scale the internet as we know it today. Not sure. If we split the addresses, we could solve these problems. So the solution space says, let's split, and it's been affectionately known as an ID locator split. So you have this kind of address, and you either have two addresses, or you take part of the address and you split it into separate pieces. There are host-based solutions and there's network-based solutions. The host-based solutions was run shim6. You put a shim layer between TCP and IPv6, and it worries about changing the locators while the TCP connection stays up. A lot of negotiation, a lot of dynamic stuff going on. People are a little bit scared of that. HIP is another way of doing it, but rather than using assigned IPv6 addresses, the EID part, or the lower 8 bytes of the address, is a cryptographic hash. And that's used as an ID, and it's also validated to be, you are who you are because of that validated hash. So the hash is passed around, and then you could build a public key from that, and then find out that if somebody is talking to me with this EID and it looks like Don's, I can use that as a hash and figure out, and if I go find a public key and say that this hash matches that public key, then I know it's Don who's talking to me, no matter where he's moving. Okay, that's the idea with HIP, another host-based solution. SCTP is a TCP replacement, so to speak, or a UDP replacement, where the connection IDs are in SCTP. So now the IP addresses as you use are only locators, and they're not connection IDs because the session ID or the connection ID is being handled by SCTP. Those three are probably the running candidates for being able to give you a locator ID split. Network-based solutions, Mike Odell had this thing called 8+8 that evolved into GSE, where it just basically said that you could split an IPv6 address into two parts, and the routing group, or the high order part, would be the locator, and the bottom would be the locator. The higher part would be locator, the bottom part would be the EID, and the routers at the edges would then fill in depending on which way you wanted to exit. Lisp is using a map and incap scheme, which I'll describe. So those are basically the classes, and so I'm looking at a network-based solution because I want it to be incrementally deployed and not have to change hosts. So splitting an address, say we have an IP address like this. Like I just mentioned, the GSE scheme said this would be the EID down here. This would be the EID here, and this would be the locator. And if a host would emit a packet, it would have to say where the destination is, because this is telling you where its current location is. So the routing group, they call this routing group, that would have to be part of a DNS entry, okay? But the source address of this packet that's being sent out could be filled in by a network device. And so the return packets could come based on that address. So in IPv4, we have this kind of address, and we can't split it up the same way, right? So what we could do, though, is today it's known as a locator, but it's also used as a hash to find the TCB when TCP is looking for, when incoming packets are coming in and trying to associate it with a TCB data structure. This is what TCP uses today. Well, if we can add some more bits, we can then have a locator ID split as well. Okay, but we don't have enough bits in a single header. So what do? So IPv6 could have a different solution from IPv4, right? GSE is rewriting the routing group stuff, and then the mapping and cap scheme, which has a separate address that's maybe somewhere else in the packet, can be used for IPv4. So GSE is kind of a NAT-like approach, but Lisp is a map and in-cap approach. Lisp will actually, one network architecture could be solved for v4 and v6, and that's kind of where we're going. In the case of Lisp, we're calling it jackup because you have this protocol stack as you see it today, and what's happening is you're just putting a new network layer underneath it. And everybody's going to say, oh, that's just like tunneling, and the answer is yes, this is what it is. It's dynamic tunneling. That's not interface space tunnel 0, you know, tunnel destination blah. It's not that. They're not static configured tunnels, okay? And that's why we loosely call it encapsulation. And what we do is the host stack operates here, so the host emits packets up to with that network layer header. So all it knows is about IDs. And then the map and encap scheme will then all it know about locators. So when you see a packet that's on a wire inside an ISP, the outside header has locators, the inside header has EIDs. So some of the Lisp goals is we want it to be incrementally deployable, no host changes whatsoever. There's no host changes to make this work. There are some modifications to a small number of routers, but these are routers that you will have to deploy, new routers you have to deploy. You don't have to change your IGP routers or your core routers at all, okay? So it is a modification of the IP architecture. It's not an enormous redesign. This is looking at a short-term solution. And I'll talk about later that this solution is being done in the IETF, where more advanced routing architecture changes are being proposed in the IRTF, in the routing research group. So we want to minimize required changes to router hardware and software. I'm getting a lot of requests from people that this may not be the case because we have to change encapsulations to do different things. I'll explain that later. But we're trying to keep the amount of software and hardware changes to a minimum. Support both v4 and v6 together, and fast time to deployment. I told the IAB that we should be able to get a pilot 1 year after that routing workshop. And I would say right now we're pretty close to that goal. We have running code. We have to decide if we could actually get it in people's hands in some decent product form. Anybody can get in some decent product form by that time. So my goal is October of this year to get a pilot deployed. Some of the Lisp parts, I'm going to break up the talk in between data plane and control plane. The data plane is the design of the encapsulation and tunnel router placement, and design for locator reachability. Is a locator up or down, even though you know that it's associated with this EID. And it's a data-triggered mapping service. The control plane is a design for a scalable mapping service, and that's what's brand new that nobody has seen yet. We have these variants for Lisp, and we did this we did this for two reasons. We couldn't make up our mind, and we didn't know what was the best solution, and we wanted to be able to phase the implementation to get experience. So if you So Lisp 1 basically says we are going to have routable IDs over the existing capital I internet to probe for a mapping reply. And I'll show you that through an example. Lisp 1.5 says when you're using PI addresses, no PI addresses will be in the core at all. But when you need to trigger a mapping reply, you send these packets over a lower performing, smaller topology that's not congruent with the capital I internet. It's another tunneled topology that basically is an ARP request over the internet, if you will, to get a reply back. Lisp 2 says DNS. This is already thrown out. Nobody wants a circular dependency between DNS and routing, so we probably won't use this. Lisa Zhang at UCLA is trying to use DNS to the protocol, but not on port 53, to be able to do EID to locator lookups. But it's going to be it's just using the packet formats and the protocol and existing code, but it's going to run on another configuration topology and on another port number. And then Lisp 3 is interesting. This is saying, well, let's build a new scalable database. Let's make sure that EIDs aren't routable. Mappings are obtained by using some new mechanisms. And I've done a lot of research on distributed hash tables to see if they can work. They're kind of interesting things, but they're really dynamic. And in an anti-third-party ISP world, they probably won't work. All the researchers are telling me to stay away from DHTs. I don't know if you guys have experiences at the routing layer. DHTs work good at the peer-to-peer layer because you do have this, stable substrate on the bottom that you could depend on. But when DHTs are changing and it's affecting your packet connectivity, then you have a problem. So Lisp comms is the control plane that we're going to introduce today. And Elliot Lear has something from Cisco called NERD, which is basically an Etsy host type thing where you actually use HTTP and you push the entire table out to all these boxes, and the mappings will always be there. So this is definitely a push-based, host-based, FTP-based, blah, 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 blah sort of thing. And Lisp comms is a hybrid of a push-pull model that we're going to explain in a second. So some quick Lisp terms, and we'll get to it. We're going to call the identifiers EIDs in Lisp. And the IDs are used by the host and are routable in source and destination sites. Okay? So the actual ID are in packets, but when the packet has to flow to the router who's going to perform the encapsulation, that ID is being routed at the same time. It's also being used as a connection ID as well. Sure, question?
What exactly is a site?
A site is, a site in my definition is a multi-home stub site, a multi or single home stub site, okay? And I would put Google and the Yahoos of the world in that classification, okay? Routing locators are the routable addresses out of PA space. Okay, these will most likely be out of PI space. This will be out of provider assigned space, and we call those we call them RLocs or just locators. And then we have these ingress tunnel routers that prepend headers, and egress tunnel routers that strip headers. Okay, pretty straightforward. So let's look at an example. So we have the source site on the left and a destination site. They have been allocated by a registry that you're going to assign all your host addresses in the EID prefix 1/8. So everybody's going to be assigned those addresses. And in the destination site, it's 2/8. You deploy these ITRs and ETRs, ingress tunnel routers and egress tunnel routers. In this example, what I'm going to show is a packet only going in one direction from source to destination. So these guys, when packets come back, they're also ETRs, but I'm just showing it for unidirectional. Okay? So you notice that they're green, so they're EIDs. These are red, so they're locators. These are actually IP addresses that are assigned to the ETRs. They come out of the blocks of their attached providers. Okay? The actual locator addresses for everyone at the site are those two addresses and no more. So now, sites don't have to allocate /24, /16, /22s, whatever, to site. They only have to allocate 2, 4, 8 addresses to the site. They could reclaim a lot of space. That could be a benefit. Okay? And these guys don't have to run BGP anymore. They really wouldn't have to. Okay, since these guys are allocating these addresses here, the aggregates that they advertise for all the sites that they connect to are just advertised back this way. So that could be a simplification, just starting off there. So let's say S wants to talk to D, and in DNS, there's an IP address, an A record that's 2002. That is an ID. That's the ID of D. Okay? If D ever moves, that's still the ID of D. Okay? And let's say the internet, the ITRs already have cached. I'll tell you when they don't have cached what we do. But if they already have cached that the EID prefix 2/8 is associated with this site, that the locator set are these two locators, and they each have a priority. They say use them equal priority with equal load split them. So this is the IP address of router D1 and router D2. And that's the mapping entry. Let's say for this example, those two ITRs already have that entry there. Okay? So a packet is then sourced by the source. It originated with its EID, which is 1001, going to the return from the DNS, which is 2002. It puts that on the network just like it does today. There's no changes so far to the host. There's no changes whatsoever. So that packet actually is going to follow the default to these CE boxes, right? That's where I said that this EID now is routable within here, but it's a scoped routable address. And routing it here does no harm because we're trying to protect the capital I internet there. Okay? So that's good because you don't have to actually reallocate. Today, if you have this site, your addresses that you're using today could be used as IDs. If they're PI blocks or PA blocks, you could use them today as IDs. Nothing at this site changes other than putting new software in these two boxes. Okay, that's really important. Incremental deployability is key. So what happens is the packet makes it all the way, say the default route is taking the hash of these two addresses, taking the default route to this place. So what S2 does is says, oh, I just get a packet it's either matching the default route, which means I'm sending it out, or there's no route found at all. Those are the two triggers that say I need to encap this in Lisp. So what I'm going to do is I'm going to put my locator, which is going to be 11001. It's 11001 out of that address space. And I know if I do an EID lookup on 2002, I'm going to find this entry in my table. So what I'm going to do is I'm going to pick one of these two to encapsulate to be the destination locator. So I'm going to use 2002. And then I'm going to ship that off. Of course, everybody in the internet knows where 12/8 is. It's provider X that's his address block. So there's no, the 1/8 and 2/8 has been removed from here. That's good, routing tables get smaller. So packets just get routed through into 12. And then when the packet comes on this wire here, it's still encapsulated. Now, since this IP address is the IP address of this guy, there's very simple code already in routers, hardware switching routers, that say if it's addressed to me, I need to peel off this outer header if the protocol types a certain thing, if it's GRE or L2TP or whatever. So this guy already knows that he needs to peel this off. He will peel it off, and then he'll then route to 2002, and then this ID is routable within here. So the IGP takes over there. And so that's the fundamental concept of Lisp data plane. We're using dynamic encapsulation, and the outside addresses are locators, and the inside addresses are IDs. Any questions at this point? Yeah, VJ.
I presume you have the transit relationship with the upper provider. So the same problem that was in USC is like, what if you have a peering relationship between the provider and the package company with peers?
Could you repeat the question for the
I couldn't even hear it, actually.
What if S&D peer? Yes.
What if S&D peer?
There's no default.
Let me hold that off until the ISP traffic engineering example, because that's more applicable for that. Go ahead.
How do I choose between S1 and S2?
Future slide. Anything else? OK, so let's look at the case now where S sends a packet, and there is no mapping in the ITRs for the 2/8 EID. OK? So in Lisp 1, what we say is, what we're going to do is, when there is no mapping, what we're going to do is we're going to copy the inner ID to the outer address. And then we're just going to route it along here. We can do that if we're using PA addresses for IDs. We should not or cannot do it if we're using PI addresses. Okay? So if we're using PI addresses and we pull them out of the internet, then you have to use this other variant of 1.5 saying, have this packet get routed in some other topology. Okay, it could be another VRF, it could be another BGP topology, but find another way to get the packet to these guys so they can respond back. Okay? So the packet gets routed through here. In the case of Lisp 1 variant, it's going to be routed through here. This guy receives that packet. He sees that the inner and the outer addresses are the same, which causes him to, he decaps, sends the packet, and it causes him to send a mapping reply in return. So what happens, he sends a mapping reply from himself, 12002, back to the outer source address saying this 2/8 EID maps into those two locators. Equal priorities, equal weights. Okay. So what it would be nice here is if the ITR could actually have all the EIDs of the world in there, so it would never have to route this thing over. Or if it could request it and get a reply back on demand, it would be nice as well, so it wouldn't have to store everything. So the nerd idea says push it everywhere so this guy never takes an EID lookup fault. It'll always be there. It'll be stored in NVRAM. It's going to change once a day. Just send it everywhere. If you do a request-reply protocol, then it's like the traditional ARP problem. What do you do with the first N packets until you're waiting for the reply to come? Do you drop them on the floor? Do you queue them? Nobody ever queues them because it's insane, right? So you drop the packets on the floor. So the question is, do you drop the packets on the floor and go send a request? Or do you actually use the data packet and try to make it on a lower performance path to get the packet actually to D? So that initial SYN message, this is the first time S is ever talking to D. So the sites don't have each other's sites EID prefixes. So what's happening is this guy could send the very first SYN packet. If you're adamant about getting it to this guy on this side, you have to route it using this, what I'm calling a data probe, either on the capital I topology or the 1.5. Now, my personal preference is we're going to throw out Lisp 1 because we want to be very strong about removing unnecessary routes from the core. So we're going to use either another topology or we're going to use a Lisp 3.0 mechanism where we're going to have a different mapping database. Okay?
And again, how does D1 know to pop the first address field? I mean, it's got a D1 when it receives the packet, it's got an 11001 address to 20002. So why doesn't it just forward the packet? Why does it? How does it know? Is there something in that header that says this is a Lisp packet? Or
It knows it by looking at these two addresses, seeing that they're the same, looking that the protocol number is UDP, and that the UDP port number is Lisp. That's what it does. And that arguably could be a host change or a hardware change. But you could also put a 200/32 in the fib to bump it up, which is dangerous because that means this guy would have to store host routes here. Or you could put a more granular route in there to cause it to be popped up. That's not going to interfere with the OSPF route that's going to get you there. Okay. But if architecturally the best way is to do what my first answer was to you, is make those 4 checks. Is inner equal to outer? Is it UDP? Is it a list destination port? If so, do this. And we also have a nonce in the UDP packet because we don't want ETR spoofing as well. We'll look at the packet formats in a second, but we wanted to give you the basic flow first. So the benefits of a locator ID split, locators come out of PA space. So we have topologically aggregatable addresses once again. I hope that's not naive to want to go there, but let's give it a shot, right? EIDs come out of PI space, so the registries could still make their money. Sites can now don't have to renumber. This is a good thing. Locators can change while EIDs stay fixed. So your mobile device will have an EID that's based on where you bought it or what service provider you're using that wants to allocate your EIDs, but the locators will change as you move. When you do ISP changes, no renumbering. That's probably where we're going to go first at the high-end side, where we really want people to be able to have the flexibility of switching service providers without getting stuck like they are today. They're stuck today because they can't renumber, and for VPNs, they're stuck because of 2547, they're stuck on one ISP. They have no flexibility whatsoever. So I'm trying to fix both those problems, actually. So roaming, no changes to the EID, you get session survivability because as long as the EID stays the same, the TCP sessions stay up, checksumming works, the TCP pseudo-header checksum works because you're using it on these fixed things that don't change. This is goodness. ISPs only need to allocate very small number of addresses to sites. We mentioned that.
Is a byproduct of that you're going to turn a whole lot of PA space into PI space? People expect to not renumber and yet have service provider portability?
I don't know. I don't know which way we should encourage it to go. It's a good question. If they use PA space, they don't really own the PA space because if they leave the service provider, they're going to want the service provider is going to want their addresses back. So.
Right, and then you get a land rush for PI space.
Right.
So in theory, you wind up with huge tracts of empty PA space from which everyone has fled.
Yes, this is true.
No PI space.
And no PI space. Well, we can, to get the simple answer off the table, we don't have to worry about this for IPv6, and then we'll say, okay, now we don't care about IPv6, what about IPv4?
TR version 2, still have my Google thing.
Right. I don't know what's going to happen there. I mean, I need you operational guys to help me with that, or at least think about it, or explore possibilities, and here are the gotchas, and here's where the economic model is going to change because of this, blah blah blah. So I'm not totally sure. So the list data plane, the encapsulation format was IP and IP, but we just changed it to UDP. The -00 spec is IP and IP. So if you get back to your offices and you look up Lisp, you're going to find the original version. We're going to publish the -01 in the next week or so. But the implementation, we already found problems with the design from the implementation, so we're already fixing the design because of it. So we decided to go with UDP encapsulation for these really important reasons. We want to be able to get through reflexive access list-based firewalls. We could do that with UDP. That's not the most important problem, okay? We want the ITR to hash on the inner header to produce a random source port when it encapsulates. So the core router that's all the way down there that has a lag can still hash and get even load splitting across the members, because that box can only hash on the outer 5 tuple, which is the source destination, and then the UDP port numbers. So the ITR is going to aid the core router to be able to get good usage of your lag. And we need to carry a nonce in there for anti-spoofing. We're going to trust that if that data probe packet gets to the ETR, and then the ETR responds back with a map reply with a nonce, it's called trusting the network versus return routability, and that's what we're going to use. Lisp would have been out a lot faster if we didn't have to worry about security, right? And you go to all the security experts and they say you need this, this, and this, and they'll say, okay, we need a PKI, you need a public-private key pair, you need a distribution mechanism to do all this stuff. The security stuff's just a total mess, and nothing could ever get deployed if nothing can get deployed without it, they say, and nothing can get deployed if you try to put it in, because it'll just take too long. So we decided we didn't want to depend on a third-party PKI, because how do you do that? You don't want to have state between the ITR and the ETR, right? So you have to, if you want to trust the mapping service, then you have to be able to, maybe the mapping service itself is the PKI, but do you want to have a separate PKI and the mapping service and the millions and tens of millions ITR, ETR flows going back and forth? So you'll see how we're going to skirt or avoid the security problem by using a chain of trust in the map reply, in the mapping database model. What we also put for the UDP encapsulation was the reachability bits, and this is how we're going to, I think the hardest problem out of all this is not the mapping service and making it scale, it's determining reachability. Because what you want to do is, now that you know you have two locators and you're selecting one versus the other, or you're load splitting based on a hash, you have to know when one of them is unreachable. And it's unreachable for a variety of reasons. The path in the internet can't get there, which is extremely unlikely, because I like to think that there's enough meshiness, enough robustness in the internet that you could probably get pretty close to the PE that's attached to the site. So what normally fails is the link, the PEC link fails, or the router that fails. Or actually, because you're running 2547, the PE is always crashing. That's another reason too. But the CE box can fail on the site side, the PEC link can fail, or the PE can fail. So I wanted to optimize for those sort of scenarios. So we had to put bits in there. So this is what the header format looks like. Let's see, did I put any? Okay, no, I didn't. So this is what, this part of the header is the IP header that the host builds. There's no surprise, everything looks the same. We're just changing the semantics of the destination and source addresses, and we're calling them EIDs instead of addresses. The term address is too opaque, too general, too vague, whatever. So we don't want to use that anymore. We want to put specific semantics to it. We try to just keep as small as we can Lisp header. So we put in a 48-bit nonce, and we put in 12-bit reachability bits in there. So there could be 12 locators per site. I'm worried about that. That might be too small. If it's too small, we'll make it bigger. There's plenty of bandwidth. I'm not going to worry about overhead if we can't support what we need to support. UDP header is as you know it. UDP checksum set to 0 on data packets. Destination port, as the packet's being encapsulated from ITR to ETR, is a well-known port. Well-known port that we've already allocated from IAMA, use it for data packets and mapping replies. We're also going to use it for the mapping service with TCP. Then this is what the ITR puts on, which is, says UDP follows, but the addresses here are the locators. I already mentioned that. That should sink in by now. So let's first talk about locator selection, and then I'll be able to answer your question about locator reachability, okay? So each mapping record will be an EID prefix, not an individual /32 or /128. So we can get some aggregatability out of EID prefixes by saying a site has one or a small set of EID prefixes. So we're assuming that the allocation is not flat or using CGA's cryptographic generated addresses. We're assuming that it's going to be, some people said can use a couple class A's, can use class D, those sort of address. I don't know if class D is kind of interesting. I mean, not class D, class E is kind of interesting to use. But the problem is there are a lot of host stacks that fail Martian checks when they look at that address and they see it's a 240.1111 and they may not do the right thing. So I'm not sure if we can use that yet. But let's just say for now that each site for the most part, can have a single EID prefix, your traditional multi-home site, okay? I'm seeing the Comcast of the world, the Googles, the Yahoos of the world won't be in that class. They'll be in a much more demanding class, as you would guess. So those addresses would be out of PI space, and then the locator list would be a locator with a priority and weight. So depending on how many locators, that's what we call a mapping record. We want the ETR to control the locator use. So we want to be able to say that if you're going to send me packets, I want you to send it on this locator more so than this other locator. And the reason you want the ETR to control is because you want to control the ingress traffic engineering. So what you say is, this is an underutilized link, and when this gets to 90%, nobody uses this link. So what I have to do is, if you can do a 90-10 sort of thing, then you can use this link or not overload that link. And only use this link if this link goes down, okay? So what happens is if you make the priorities all the same, then the ETR is telling the ITR is, these are the valuable links you can use that I want you to use. And you could decide within them which you want to use. So the ITR also has some control as well. So there's some flexibility there. Now, for mobility, you may want to glean. You might want to glean when you get a packet in and you've never talked to that guy. You might want to take the source locator and store it and associate it with an EID and an EID prefix. So then when you send packets in the other direction, you don't have to do the lookup. Or if that's an exception list to what is in the EID mapping for the mapping service, you might want to use as an override, right? If Don is sending me packets right now and his EID is out of the Google space and his locators are for the locators that for the ISPs Google is attached to, and Don starts driving and then and goes to Starbucks and now starts sending from Starbucks, I'm going to see that his EID is coming in from a different locator than what I have in the mapping database. The mapping database tells me that Don is at Google and here are the set of locators, but I just got a packet with a different locator there. That might be a roam event, an insecure roam event, but a roam event. So the ETR could have these exceptions. It's not host routes everywhere, it's these exception routes only in the ETR. Can we make this work? So we're trying to figure out how fast of mobility we want Lisp to solve. And right now we're claiming slow mobility. So camera, slow mobility, okay? No fast mobility. Okay. So locator reachability, that was one of the questions. It's imperative that locator reachability is not in the mapping service. We want the mapping service to scale. And so we can't have changes that happen often. So we're saying that the mapping service is a subscription time mapping, where when you set up links and you do EID allocations, that's when you put it in the mapping service. It probably shouldn't change as often as DNS entries, less often than DNS entries, okay?
Well, so it's going to constrain one of your bells and whistles, which is the constant traffic, right? So there would be some people might want to be doing rapid traffic engineering, and that's going to be based on this mapping, right?
You have to decide that for large equivalence class of flows that's going to use one Lisp tunnel versus a different Lisp tunnel, if that information needs to be in the mapping service, or is it just plain old static? That's all. You have to decide, right? Now, the mapping service that's provided there doesn't need to go in the capital I mapping service infrastructure. It could be a map reply that does this data triggered thing. Because you see, we have this data triggered way with the map reply, and then we have the mapping service way, the control plane way. So we have to really figure out, look at the really gory details to figure out what's the best suited for the traffic engineering piece. So how do you know a locator goes away? We're assuming that locators that are in the record are all reachable. And let's say that the glass is half full and we keep it reachable and we use them. What you want to find out is when they go unreachable. Well, you might, we're not going to depend on it, but you might get ICMP network or host unreachable messages back from somebody in the network. Well, usually that's not going to happen for two reasons. One reason is if a locator goes unreachable, and it's probably not going to result in an unreachable message going back at this box because that address has been aggregated. So really, in the core of the network, nothing goes away. And there's no opportunity to send ICMP unreachables. If you think there's an opportunity to send it, everybody configures to turn them off. So, so I'm not going to depend on that. And that's in the middle of the network where something go unreachable. Really, like I said, the CEP link, the CE box or the PE box is going to go down. Okay, and that's why we're putting these locator reachability bits in the data header. We want return traffic to tell you about the reachability of the ETRs. Okay? So think of it this way. I'm an ETR at a site, and Scott's an ETR at a site, right? We both know if we're ejecting default route into our IGP, right? And it's usually based on having this interface up to the ISPs. If one of those interfaces go down, we withdraw our default route. So I will know that if the PE link goes down from Scott's point of view, or Scott crashes, me and my IGP will know that Scott's not around. When I start encapsulating packets, because now everybody's going to be sending me data here because I'm the only default router, right? So I'm going to be getting packets here, and I'm going to be encapsulating as an ITR to the destination sites wherever. Well, everybody who's gotten the previous mapping for us, I'm just going to say that, okay, I was ordinal 0, you were ordinal 1, so we're going to set bit 1 and bit 2. So the value 3 we're going to send across. When Scott goes away, I'm going to set the bit 1, just saying that one. They're going to look and say, there's this bit string that's describing the reachability of all the locators that have been previously advertised to me. There's Dino, and Scott is in the list that was advertised to me. Dino is telling me Scott's not there. So then when the ITR wants to encapsulate data back, only uses me. So it's data plane piggybacking. Anybody, so the person who, did you ask a question about reachability? Did that satisfy your answer?
My question was different.
Okay.
It was how do I decide which ETR to use?
Selection. Okay, that was based on this slide. Maybe I didn't make it clear enough, but you know, I didn't say anything about it. So what happens is, I give you a map reply. You have these list of locators. You will look and only use the high priority ones. If you have more than one high priority one, you'll use a hash if you want to round robin them against it. If you have a policy to say only use one, you can use one. The one that you decide to use must be up based on the advertisements, the piggybacks coming back. And so if there's something like, let's keep it simple. Let's say there's 1, 1, 2, 2, 3. Those are the priorities. You have a locator that has 1, 1, 2, 2, 3. So the ETR is saying that you can only use the first 2. And only if the first 2 go down, you can use the 2 that are in priority level 2. And you could decide if you want to load split across the 2, use one versus the other. As long as they're both up, you can do whatever you want as an ITR. Okay? If those 2 go down, then you only could stay within the 2. So that's how the selection is done. So this is kind of a not so sophisticated, very loose form way of doing some policy but not going overboard. So let me know if you think this is sufficient.
Actually, the original question was how does so the host sends out a packet
Yes.
with EIDs. It doesn't know anything about locators.
Right.
How does that packet inside the site, inside the source site, how does it get routed? Right.
It follows the default route as it does today to the edge of the network.
So it goes.
Because the destination address that the host put in the DA field, there's no specific route. If there is a specific route and if you're BGPing inside, it'll follow the shortest path out. And that egress box will actually be the ITR and prepend the header. If it doesn't have the more specific route, it uses the default to find the edge.
So it'll go to the closest ITR.
Yes, and that's based on your IGP policy on how you want it to exit your network. What you're using today will be the same mechanism you use for this.
But basically, any host will use the same ITR all the time. It won't depend on which destination it's sending to.
It depends if you have more specific routes injected in your IGP or you're using active default routes. If you're using active backup, it's going to go one way.
But you're not injecting the locators you're not injecting the EIDs from other sites into your IGP.
And if it's from PI space, you won't be able to because they won't be there. Good point. So you can only resort to the default routes inside the IGP routers.
The closest box, right? You'll only get to the closest edge of the network.
Yes.
And then you'll go to the closest provider, and that provider will deal with all the traffic.
In a multi-home site, a stub multi-home site, you will go to the shortest exit. Okay?
So you're trading egress to E for egress.
You're trading egress.
Trading egress, you're trading the ability to do egress to E for ingress to E. So if I'm
No, it's not a trade-off. It's not a trade-off.
Well, if I can't carry those routes, then I can't do egress to E on them. Right? So you're saying I'm not going to carry anything.
No. Okay, so this is Google talking, right? Google wants to inject all the routes into the ISP, into your site. If you inject it in your site and you have locator addresses that are sending your IGP, what you do is you move the ITRs closer to the host rather than the edge. And then you get those locator addresses put on the packet sooner, and then you get what you want, okay? I see, okay, I see where you're coming from. You guys have the whole internet in your routing tables. You guys are the whole internet. Okay. Okay. Did I answer?
We can either confirm or deny.
Right. I wonder if you type in who owns the internet in Google search, what you get in response. Can you fix that before I get back and try it? Yeah. Okay, so one quick word about transition issues. In any brand new design that you're trying to do, you have to worry about what's not out there, right? So if a Lisp site wants to know that there's no ETR at a non-Lisp site, it really doesn't know. There is no protocol that's taught ETR to ITR stuff. It's just encapsulation. It's trying to be stateless in terms of the connectivity. You know, there's no security associations between the two. So the only way that you know that there is no ETR there is by testing it using a negative test. If you do encapsulate and assume that there is, because you think that this is the locator address for a particular site, but it turns out to be a site that is using just what it is today. So the packets are actually going to go straight to the host. But the hosts don't have ICMP port unreachables turned off. So those do come back to the ITR. And then the ITR could put negative cache state saying, this is not a Lisp site. Any future packets that come through me will not get encapsulated. Okay, so that's great, because now you can get the packets all the way over there. Now the packets coming back can come back if my source locators are PA addresses, right? Because that means they can route back. But if my PI addresses, they can't get it back. So what my ITR has to do is know that a site is not Lisp capable, and if it's using PI, that it has to source NAT the packet. It has to change the address to a locator and send it back, which means it has to change the TCP checksum just like any other NAT device. That's the how we make sausage, basically.
Who can I cause to not be able to talk to who if I spoof a lot of ICMP port unreachables on the well-known Lisp port?
Yes, good question. No solution yet. Oh, I did, the preamble was, let's don't talk about security. Because once you claim you have it, you don't, because there's always something that could circumvent it. So we're just going to say we don't have it, and you can circumvent it in any way. But we have to figure this out some way. So let's get to the traffic engineering. This might be more applicable. We can have these things called TE-ITRs and TE-ETRs that are deployed by consenting peering ISPs or large hosting vendors. And you can take these large equivalent class flows, like bunches of prefixes that you know of today, and associate them with the tunnel, and then encapsulate it. And then you don't have to use the BGP policy per prefix, per customer prefix. You just now have to use the BGP policy for the single locator, okay? And then you don't inject more specific routes. So here's an example how it would work.
I'll apologize for this in advance.
Sure.
Go back to the previous slide. If you're going to call one Teeters, you really have to call the other one Totters.
Teeters and totters, okay. Okay, that's the best comment I got from you today, Stephen. Teeters and totters. Okay, so we still have the same situation we did with EIDs on each of the sites. We still have the same locators. But now what's going to happen is the provider B and provider X want to do some TE stuff. So let's see how it could work. So the host emits the packet just like it did before. The default route follows it down through there. Okay. Okay, I want to be reactive to your question. So if this 12002 was injected into here, the ITR would be here, and then this packet would be floating around here, so you can inject more specifics to address that question. So that would work fine. But the packet appears encapsulated there on that egress link. Now what happens is B1 would normally send it to the red link, right? Because that's where BGP would tell it to go. But that red link is a little bit overloaded. But these green links are unutilized. I mean, B doesn't know that this Y to X link is underutilized, but it definitely knows that its B to Y link is underutilized. So what it does is a TE-ITR saying, I'm going to put on another header, and I'm going to say which way I want to go. And if it puts on this address that can either be dynamically determined via a map reply or statically, it can know that the BGP policy for this specific /32 is maybe this way. So because what's happening here is provider B and provider X have an agreement that they wanted to use these inter-domain traffic engineering tunnels, okay? So we know that intra-domain traffic engineering tunnels work with LSPs, with MPLS LSPs. We know that there's a way you can circumvent routing to take packets, and that's what MPLS does. What we want to do is pick it up a notch and say we want it to be inter-provider because we want these links to be more utilized. So what we can do is we can say that anything that comes in through this port, if B1 was having this T stuff coming in through here or through some, say there's thousands of sites or hundreds of sites that are coming in, somewhere in the middle of the network, they can say everything that's coming in through me, I can go ahead and just encapsulate and send it through some other path. Okay. Now, that we already mentioned this, we don't want to put that in the mapping service, so we think that the data triggered event may work, or it could just be flat out static. TE tunnels are static, right? They're somewhat static, which means the length or diameter of the tunnel, hop by hop, is configured statically, right? And then you have a protocol that actually builds the LSP. That's not very interesting. And then use these IGP shortcuts and you bastardize the IGP to make it use those paths, okay? I'm not sure if I want to bite off and say, let's have BGP treat this as a separate path and use it, i.e. the tunnel. But this can be made actually more secure than the ITR to ETR connection because you can use shared symmetric keys here, and you could then encrypt all the data going back and forth like an IPsec tunnel. Okay. And you'll be able to get your load splitting because this guy here will then look at the UDP packet, that's the UDP header here, and we'll be able to generate another UDP header here, so these lags that are built inside here can get good equal cost load splitting. Because the big problem with doing tunneling is you've taken all these 1, 2, 10 gig flows, and you made them look like a very large flow, and because the source address is coming from one point. So we have to be able to figure that out. So the packet comes to there, that X1 decapsulates it, he forwards it. So there's basically 2 levels of tunneling here. Now, we're only going to support 2 levels of tunneling and no more. So this is kind of an MPLS label stack of 2 and no more. And it's important because there's a lot of overhead that's associated with this. And you don't want to have too much, you have to worry about looping. So the first check that's done in the forwarding path is how many levels there are. And if somebody does screw up something with static routing, you always copy the TTL from the inner to the outer, and then from that to another outer. And then when you decapsulate, you copy back into the inner and back. The TTL is preserved from source to destination. You have to do that, or there's all kinds of loops that can result, forwarding loops. Yeah.
As an emitter of a packet here, if I've picked an MSS for something like TCP, and I don't know that stacking is going to go on, you've got a fragmentation and reassembly problem.
Right, right. You have to, if you use MTU discovery, you have to respect it. If you don't want to depend on it, the receiving side will have to know that it gets lowered and tell the other side. That's a host change that I don't want to bite off. The bottom line is if
WAN5 becomes really popular and nobody tweets up their MTUs, and now we're 1,500 bytes in the core, right?
Yeah, see, what we're depending on at Cisco is that everybody continues to use GigE and using 1,500 bytes, and then we use 9K everywhere else. So we think it's less of a problem. But if you use 1,500 and 1,500, you have a problem, or 9K and 9K, you have a problem, right? I mean, this is nothing new. I'm not introducing anything new. Tunneling has these disadvantages, right? And we have to just figure out how to do it. Now, MPLS has the same problem, but it's usually 4 or 8 bytes that's added, so you don't hit the error part as quickly. Go ahead.
So in provider land, you already have these BGP peering relationships. Why not use it to signal these? I mean, why create these role routers when you can kind of just do ubiquitous?
You can, but when you change BGP, you have to change it everywhere. And you have to really be sensitive to that. Any change to BGP takes 2 years to get deployed everywhere, if you're lucky. Incremental deployment. I mean, we have made really hard decisions to keep it incremental. And nowadays, if you want to do anything new on the internet, it's over the top. No kidding, right?
It's a new address family that you can negotiate, and you either know how to, you either can speak it and negotiate it, or you don't speak it, or you don't negotiate it.
You got to do it. You have to do it end to end, though.
The whole thing.
You have to do it end to end.
You know, if you're going to use BGP for it, you might as well just give everybody /24 and have BGP do this thing.
So to be, oh, well, you certainly can do that. If you think there's local scope, I mean, you still have to upgrade all the Sprint routers and all the Verizon routers to do it, and that's still a mammoth project too, okay? Or just going to Verizon and say, upgrade all your routers to do BGP is a mammoth thing to do, let alone interdomain, let alone capital I internet. But to be sensitive to your thing, it has already been thought about that on this Lisp 1.5 topology where we want to move around EID to locator mappings, that we could have a new NLRI in BGP and use it on a different topology, but it's a different topology. It's not on the existing routers that are moving data quickly.
But we did it for 2547 VPNs, we did it for IPv6. It's just a new action.
Took 5 years. And maybe the proper response to your question is maybe we don't have to hurry. Maybe it's not urgent. Maybe 5 years is okay if you think it's better. I mean, it's all these sort of trade-offs and hard decisions you have to make and crystal ball, predictions. So it could work. I mean, there may be people that will want to do more things in BGP because it feels comfortable. They have the knob. But I know that doing this mapping service thing, the BGP is too big a hammer for the problem. And BGP has problems that, wouldn't it be nice if we could fix it and go to a next generation thing? So, yeah. So that brings us to this.
Can you hack BGP to do this?
Yes. With enough thrust, anything can fly. And everybody knows, the older guys in here know who coined that phrase, right?
In the sense that you would use arbitrary stuff in the well-known attributes that are already transit and are guaranteed to get to your rank. And you could, I don't know if you've thought about this, you could put magic in the prefix field. And originally
You're absolutely right. So what you have to do, if you wanted to put a mapping record in a BGP update, you have to build a new NLRI that has to be exempt from doing BGP path selection, right? Because it's more of a distribution. You don't care about the shortest route to the EID prefix. You just want to get them everywhere, right? And really, we don't have, this perfect segue into this. So we don't really have a database infrastructure that gets a lot of pieces of information everywhere. And when I say get it to everywhere, means push it, right? We know that we have one very large and scalable database called DNS, but it's an extremely pull and TTL timeout model, and we know it's hard to update, right? So we have to decide, do we want a database that's easily updatable and push things out? Because if it was, and if it was scalable, now this is really, panacea, and I'm smoking something by saying that, is that it wouldn't be great if we could push out everything and all the ITRs had all the mappings, and when the locators came and went that we told them what the new mappings are. This ain't gonna scale, right? So let me continue, and then maybe I could pacify your question.
I need to, sorry, but I need to, I'm curious at your assertion that you can't put stuff into the DNS fast.
You could put it into DNS fast. You can't get everybody who has a pointer to the old information to get updated fast. That's the problem. There's 1,000 people that know what your locator is, and you just changed it. Now, how do you get to those specific 1,000 people? The new guys will come and get your new information. The old guys have to TTL timeout. Now, you could push the TTL 0 timeout everywhere. It ain't going to scale, because you got to push it everywhere to find the 1,000 guys. Make sense? Yeah. I mean, this is nothing new. This is, large scalable distribution protocols. So we want to build a large distributed mapping database service. It is not a routing protocol. I repeat, it is not a routing protocol. It may look like a routing protocol, but it is not. And we are keeping it as simple as possible because I have to implement it, okay? Scalability is paramount to the solution. So how do you scale? This is I'm calling this the new Tony Lee formula because he just brought it up. It was elegantly simple, and it's like, no shit, of course. Well, if you have a lot of state and you have it changing at a rate, both of those factors are really large. You have a real big scaling problem. But if you can control one versus the other, you may not have a scaling problem, depending on the size of the other factor. So we think the state is we're going to shoot for 10 to the billion, or 10 to the 10th, which is 10 billion, right? We're going to shoot for that many hosts. We're not going to shoot for that many entries in a database. We're going to try to aggregate that to a couple, to many orders of magnitude and see how it works. And of course, we don't need that in everywhere, okay? So what we'll do is we'll aggregate EIDs, the actual ones that are assigned to hosts, and the EID prefixes, as I mentioned before. That's the first order of reducing state. And we have to keep rate low. And that's why we're saying that the mappings are subscription time frequency changes. Okay, really important. So mobility will not be solved with this solution. We have to figure another way. So all the big questions asked is, where do you put the mappings? How do you find the mappings? Is it a push model? Is it a pull model? These are all the questions you ask when you want to build this large scalable distributed database. Do you use secondary storage? Because there will be a lot of it, but maybe memory and disk is cheap. Maybe you can store all these entries, right? Do you use a cache? What about securing the mapping entries? Oh boy. What about protecting infrastructure from DOS attacks? Oh boy, these security things are nasty. What about controlling packet loss and latency, trying to go get the information? So, push doesn't scale, caching doesn't scale, pick one, okay? So we're gonna pick both of them. We're gonna do a hybrid approach, okay? So push at upper levels of the hierarchy. We push at upper levels of the hierarchy because we think at the upper levels of the hierarchy, we can scale the number of table entries to be really small, okay? At the lower levels of the entry, you don't want to push everything there because not everybody needs everything all the time. So they're going to pull what they need and they're going to cache and they're going to time it out. We know caching works to a certain extent. DNS is an existence proof, okay? Mappings stay at lower levels. So we have these mappings that stay at low levels for the part of the internet that they're going to be responsible for. And we're going to send requests. And if we find the guys at the first level, that's great. If not, we're going to route the request to where the mappings are going to be in return. Okay? So listcon is not a DHT, but it looks the way the request is being forwarded. It looks like you're trying to find the node on the distributed hash table that maps to the key that you're trying to do lookup data for. It is not a DHT. It's a Lisp 3.0 variant. So we get good EID prefix aggregation. I'll explain how it all works with a picture. I'm past my time, by the way. You want me just to keep going through? Okay. If hierarchy is based on EID prefix allocation and not topology, we can get good aggregation. Okay? This topology that we're going to build is going to be an EID allocation topology, and it's not going to change often. It doesn't have the effects where you put a backdoor link between Verizon and Sprint and everything changes. We're going to force the semantics to get scalability. Okay? So we're going to build this logical topology based on EID prefix allocations. Map requests will follow the logical hierarchy, and the key to be used to find the data you need is the EID, and the map reply will return the record. So we'll introduce these two components. So Lisp, we're calling the protocol cons because we're bringing the data plane and the control plane together. And we're calling the first level of the hierarchy content access routers, or CARs and COOTers. So you old Lisp programmers are part of the, we're using some of the terminology. And it's somewhat fitting. We did put authentication up there, right, which we still might use, but we didn't want to focus on the security aspects of it because there's tons of holes in it. So anyways. That, maybe we should implement Lisp in Lisp, yeah. Anyways, we're going to hold the mappings at level 0 of the hierarchy. It doesn't mean each level 0 node has to hold the entire mapping. It's just going to hold the mapping of the sites it connects to. And so it will be in the power of 2 block of those sites that are getting those EID allocations. So, and then you aggregate EID prefixes as you move up the hierarchy. And then you generate map requests and respond with map replies. I already said that. The COOTers themselves are doing the pushers. So the CARs at the bottom are doing the requests and replies. And then the COOTers at the higher part of the level, they're going to push around the EID prefixes in an aggregatable manner. So let me give you an example of that. So we have some sites down here. And we have ITRs. These are the guys who need the data to find out the location of these guys to encapsulate packets, right? So what we have is we're going to have a huge number of CARs that are going to aggregate lots of sites. The first level of the hierarchy, we're going to call it level 0, okay? And then these guys are going to have these parents, which are the COOTers, and the COOTers actually push the data around within a mesh, but then they have different levels that they will then aggregate prefixes going upwards. So we have level 0. We're going to start numbering the levels here, and as you need to make it scale in the future, you add levels to the top, and you just do a +1 for the levels. Okay, go ahead.
In this picture, can you explain to us a little bit, like, if Don is below ETR1 over there?
Yes.
If he moves to ETR2, how does the information propagate?
I will do it at the end because that's a mobility situation. That's mobility.
Who operates that?
Let me explain it first, and we'll talk about the operational stuff. And that's the kind of input. That's the kind of input I want to get from you guys. In short, I think the CARs can be put either at IXCs, they can be put at registries, or at ISPs. I really think that, you have your DNS server here. That's what the ETRX is. This is your first level DNS server that you use. Where's that DNS server today? It's in an ISP. Where's the second level one, a root server? So it's really only 3 levels of hierarchy. I don't think it has to be much different than that, but let me know what you think. I'll be around after this if people want to help me see the light, so to speak. Okay, so let's say we have this, this guy right here is this EID prefix. It's been allocated to the entire site, and the locator addresses are L1 and L2 right here. So he keeps a table. This is supposed to be a table, even though it looks like a newspaper. He keeps a table there. Now, the first thing we did, and we pulled it out of design, is we want him to register it up here. And we realized if we wanted to register because we wanted him to be able to give him the public key, and then when he registers, he would then sign it with a private key, so this guy knows that this guy would give it to him. But we said, let's start off really simple. Let's configure it here. Because if you configure this thing here, this guy, or maybe this organization is allocating that to him, will then have to configure it in here to make sure I sent this guy, because he's going to configure this peering relationship. He's going to say, I gave this thing to this guy. Now I got to make sure that guy advertises it back to me. So it's just like, I'm telling you something. Now I have to put an ingress filter to say that it's the right thing. Well, just have him configure it, right? This guy's motivated to get this site online because he's paying him, so to speak. Talk about economics later, but maybe there's some motivation. So at front, we were saying this mapping will actually be configured here. So what's going to happen is this guy calls up the registry. Say this is Aaron, right? And Aaron's going to deploy a car. He's going to say, I need some EID prefixes. And he goes, OK, I'm going to give you a /24. It's 111. And he goes, OK, thanks a lot. Here are the locators I'm going to use, because they're going to be IP addresses that I'm going to use. These IP addresses that he uses is based on his ISP connections. This guy doesn't know that, shouldn't have to know that, shouldn't have to keep track of that. So he's going to say L1 and L2 are my locator addresses. He says, OK, so I'll put in this entry in there. And so when I tell people that when they send encapsulate packets to L1 and L2, it's in fact ETRs that can encapsulate it, okay? So this guy has similar, and you notice it's in the same power 2 block. If this guy was not in the same power 2 block of this guy, he would not attach to this car. He would attach to the car that has the same power 2 block. We're going to force that. A logical topology here. This is just a TCP connection. We can do it. We have no restrictions at the physical layer anymore. We have these business things that we have to worry about that I hope will be okay, but we don't have any physical limit restrictions. So now that this car will keep these 2 mappings, so these 2 mappings are just sitting there, right? What he's going to do is, because he has the next level up, when he has a peering relationship with this CUDR, he's then going to aggregate. So anybody that's in 111/16, no matter what registry anywhere in the world that's going to say, I'm going to give you something out of 1116, they're going to tell them the only way to get on to the internet is that you have to open up a TCP connection to this guy. We're not going to let you come in here because we don't want the more specific to get injected. If we let more specifics get injected, we're at flat routing again. This is bad. So this guy will have the same thing, and he's going to aggregate them for the next set of cars that come into him. So as we see, the aggregates just go all the way up to the highest level. Now, this is what I've learned working 25 years in the internet. You never have one guy at the top, because everybody wants to be at the top. It's going to be a mesh. So all the big 4 guys, they're going to be in a mesh, and they're going to peer with each other. Okay? This is good. And now, within a mesh, what happens is we're going to enforce that these boxes all have the same mask length. So nobody can advertise, you better not have a /16 come up here if this guy has a bunch of /8s coming from other CUDRs. This guy's going to reject it. And we're going to try to make it auto-aggregation. So we're going to make sure that this hierarchy stays intact. This is an EID allocation hierarchy, right? Not a packet forwarding hierarchy. Data packets never go on this topology. Only requests for EID lookups go on this topology and replies.
What do you imagine of the other 3 people I'll need to talk to up there?
Okay, so I should start putting some logos up there. So let's say the ITR sends a packet down here. This guy will send a map request for who he wants to talk to. Maybe somebody, 1111, so it's somebody in here. He got that from DNS, okay? And then what happens is this guy, let's say, has no mapping up here. He has no mapping, so he's going to forward it. He's going to forward it because he doesn't have any specific route at his layer of the hierarchy. So what happens is this guy always forwards to a parent. What we're going to do inside here is anybody who has a parent relationship injects 0/0. So you'll either have at this level, it's /16s or a /0 and nothing else. If you have a /16, you know that the request is for one of your peers, and then you'll route it within here. But if it's not, you send it up, okay? So the latency increase, if you want to connect to somebody far away, your latency increases because you're going to do this hierarchy. I don't think this hierarchy is going to be many levels, okay? We look at DNS today, and we're at 2. Maybe we'll do 3, I don't know. It doesn't have to be a lot of hierarchies. So what happens, he doesn't have the request, so he forwards it up this way. Now this guy up here, since he's at the highest level of the hierarchy, he's going to find the shortest path to 1/8. He knows 1/8 is in his tables up here because this was aggregated, right? There's going to be a good chance that these routes are going to be, don't call them routes, these entries are going to be very stable because there's a lot of crap under /8. This /8 will probably never be withdrawn. That means route stability. This is good, right? So so this guy pushes it to his shortest path, which he thinks is that cooter. This cooter says, I'll send it down here. And then now it's flowing downstream based on the more specific routes each time, just like IP routing is done today. This car gets it and says, I have the mapping for 1001 or 11111. So I'm just going to send the reply back. He sends the reply back. Oops. He just sends the reply back. And the reply is actually routed back the same way. So when this guy sources the request, he sources the request from an EID that's part of this aggregatable range so the packet can flow back. We're putting path vectors in the request and the reply and in the advertisements. So when you look at a table, you'll see the paths of what's happening. You don't have to have another tool called traceroute to do it. So you will find out the path the request takes and which path the reply comes back. So the tools will be embedded in the protocol. What I've also learned in 25 years is you don't build a protocol and then worry about management later. You build the management capabilities inside the protocol at the same time. Okay, so just quickly how this thing works in a little bit more detail. So you have these lines that I've been drawing here. These are all peering, they're all peering on TCP HMAC protected connections. We're going to make the implementation say if you open up a TCP connection to me and you don't have MD5 or SHA-1 as the TCP option, connection does not come up. We're going to require a peer-to-peer authentication that's going to happen. Okay? These guys are regarded as sibling peers, and they're configured as such because they're in the mesh. This guy's a parent peer because he has a connection to a child peer, and that's where you know what the layer boundaries are, the level boundaries are. Okay? And then this guy, what his responsibility is, since he's a child and connects to another level, he's responsible for injecting or pushing 0/0, so anybody knows how to get up. Okay? And then he aggregates going up. Those are the only rules. This is going to be a simple implementation. I'm going to try to do it in 2 weeks. Okay? I always try to challenge that way. Within the CUDA mesh, you just push entries, and we're going to push entries like a link state protocol. All that means is we put a sequence number in the packet, we push it out all our links. If you see a duplicate sequence number, you don't re-forward it. Okay, and then we have a path vector along the way. You use the path vector to find the shortest path in terms of number of boxes. Simple hop count. That's it. No more. It's not a full-blown routing protocol. We're not running a Dijkstra. We're not doing split horizon with poison reverse. We're not doing the dual algorithm. It's just a simple distribution protocol. Okay? The shortest path shouldn't matter. I believe, and tell me what you guys think from your initial gut reaction, I believe these connections will be relatively stable because these are TCP connections between 2 points in the internet, and there's a lot of robust connectivity under here that's going to keep that connection up. Again, the only time the connection is going to go down, turn the camera off, is when the Cisco box crashes, right? But other than that, these connections should stay up. So I think it's a stable hierarchical topology not used for data that can be sort of stable and stagnant. That's the goal. So just in the car, it's very simple. A car is just a special case of a CUDA, but it holds the mappings, right? And it has the same sort of attributes as everything else. And then the parent's there, the child's there, and then it does, and this is an HMAC protected thing to the site as well. So do we have security in the mappings? It's a chain of trust through this hierarchy, HMAC protected. Is it good enough? Keep going.
Well, if any of those boxes is a box,
each of the green things is a box. It could be a Linux box. It could be a router. It could be a host.
then upstream we have to be talking to two.
Oh, no problem. Yep, no problem. I was going to put the hierarchy in, but I thought it would make it too too messy. But that's a good comment for the next revision. That don't worry, there is redundancy built into it.
There's a picture of widespread renown within the company here that shows a data center with a fire truck outside, saying that all the reliability inside doesn't matter. When the fire marshal comes and says, what's the building, it says, turn that off.
Yep. You aggregated all your redundancy. Yep. Okay, so winding down. So this is what we published in January, and this is what's going to be updated to do this sort of thing. We should have that out in a couple weeks. This should be out by the end of the week. Dave and I are working on it right now. This is the mapping service. This is the encapsulation service. We have a prototype available. I did a prototype of the data plane version first before we were working out the mapping service. I've tested it in my lab. I have it running on DCOS, which is another operating system Cisco is working on a PC platform. It can work on these other platforms too, but they're platforms you probably wouldn't buy for this purpose. So we have it working. Dave Meyer and Vince Fuller are now taking it and doing internal testing. These guys are really good because these are ex-operators, so they know where things break and they know how to test. I've used them for beta sites like 15 years ago, actually. So they're testing internally. We want to start some kind of small external pilot, which is a very well-focused set of people that want to work on it. If there's anybody here that has cycles and wants to be involved in this, I'd love to get you guys involved in it. And then my next step is to then start writing some code for the cons, the Lisp comms part. The standardization, Lisp is doing the engineering stuff, so people think that Lisp should be in the IETF, but more long-term architecture stuff should be in the IRTF. And then the Lisp cons part of it is part of IRTF as well, or the RRG in particular. And this entire effort is completely open and IPR free. That was the commitment we made at the IEB workshop, that there's no proprietary stuff going on, no patents or anything. This is kind of pro bono, philanthropy, whatever you want. We want to help the internet. And there's a bunch of us that want to do this now. So what do we want from you? If you could review and comment on the drafts, that'd be awesome. Devil's in the details. We want to get the details right. Give us requirements, keep us practical, and if you're interested in beta testing anything, just please let me know. And Lisp rules. That's it, I'm done. I was 25 minutes late, sorry.
You had one slide on this that was too fast, so forgive me if you covered it.
Do you want me to go back? I can.
No, so the question is for an early adopter, whether it's an endpoint or whether it's a core carrier. For the first adopter, obviously they're going to do some work there for this pain. What benefit does the first adopter get from it, and how does it work at that point?
Right. Well, the first adopter will be able to get benefit by going to get a PI address, being able to renumber, and doing that until other people can do it. So
They can do that now, though, right?
They can do that now. Basically, a locator ID split is implemented today in all NAT boxes. It is. So there is motivation. But it's like anything. Anything you introduce that's new. There is motivation, but how do you get the first? I mean, why did we go to BGP4 when we did? It wasn't very motivating because people said we could build routers with more memory and just make it work. And do flat routing and just make it work. There were a set of people that got together and said, this is the right thing to do. We want to be efficient. We want to lower cost. And we have to thank those people that the internet would be a mess today if BGP4 wasn't implemented. A lot of people would like to get rid of BGP4, but just think if it wasn't there. So I mean, I don't have this solid response to you. Just saying it's just the right people have to get together to provide the incentive. Hopefully there's some business models that can come from this. There's new infrastructure. And whenever there's new infrastructure implemented, everybody says, I could sell and do this. I could provide a car service. I could provide a cooter service. I could be an EID allocation entity. All of these things spring up as revenue sources potentially. So that's how the infrastructure guys will provide. How will the end site benefit is, same reason why IPv6 is not deployed. There's not one killer thing that's totally obvious that it gets everybody to do it. Will we eventually get to IPv6? Probably. We probably will get there.
Okay, you actually hit the nail. My real question is this ever going to be real? And my answer for IPv6 is, for a while, then no, not in the next 5 years. And I'm not sure if that's right anymore. I've been watching quite as closely. So,
Well,
yeah. Maybe, some carriers has to decide they're going to do this. But it seems, so at what point how much has to be implemented before somebody gets a benefit?
Right. I think, unfortunately, I think if you want to look for like one killer app or one killer reason to do it, it's going to be mobility, which I had major disclaimers against, right? I think that's the biggest one right now. Because everybody's doing locator ID splits sort of thing anyways with mobile IP and mobile IPv6 and NEMO and all these different ways of doing mobility. And so it's kind of already there. The question is can we have one solution that really kind of fits all these different environments? If you could solve a fast mobility case, it'll work for ISP change case, right? So I don't have a magic answer. I mean, me as a protocol designer first has to make it simple and convince people like you that it's actually doable. And hopefully the concepts here weren't too advanced or you didn't see any non-starters. And I have to get past that before I can look at the business models and the motivations. And that's why we need more operational and people in the art, so to speak, that do this for a living to help with that aspect of it.
So the benefit here is that you can keep the internet keep scaling without router tables having bigger and bigger. How many folks have to adopt it before they start seeing that benefit?
You also have to define what's benefit. Is benefit looking at one particular router and seeing that it has 100,000 routes instead of 200,000 routes? So it's hard to say what's benefit. The way it's worked in my career is you build technology, people find a way to make money off of it. That's benefit. I'm building another tool in the toolbox. I'm not sure if it's the end all. I'm not trying to say it's the panacea. We're just looking at real technical problems and trying to solve it and creating opportunities for people to use it in different business model ways. I mean, it's as humble as that. I mean, I don't know what else to say, I can't give you the answer that you're looking for. I wish I could, but I couldn't.
Well, I mean, the only problem with touching on a point is that one of the key benefits and focus is reducing, route table size within the core. But but in order to get that, you basically have to, the people who are at the edge of the network have to implement this on their network.
Right.
Right. I mean, so the people have to have the ITRs, the ETRs in their stub networks in order for this
right.
to work.
I
mean, they get a benefit because if you really work this, if this really exists, like fairly ubiquitously, that ITR and ETR could be pretty simple, right? I mean, it doesn't have to do a lot of stuff.
Right.
Standard stub networks with a couple of exit points.
Yep, you got it.
You don't have to engineer, inside that network. So there may be a benefit for them, but it seems like one of the large parts of the benefit of this protocol is that you're reducing your route size, route table size in the core.
So you see that as a benefit.
The core isn't carrying that, right? They don't have to do anything in theory, right? I mean,
right. That kind of scares me a little bit because those are the personalities that could help deploy this, but now that they're not involved, they're going to say, oh, it's not my problem. Now, I presented where you can use Lisp ITRs and ETRs at the site. There's no reason why you couldn't put them at the PEs. I don't think that's the best place to put them for scalability reasons, because I think I've always had the mantra that VPNs always scale better at CE devices than PE devices, and it's proving true with 2547. So you could do this at PEs, and you could have an ISP provide this sort of locator ID split service for. And if somebody like Sprint's going to build all these mobility services and have this WiMAX spectrum that they're using and everything, that they may be motivated to put these things in there and offer it as part of their service. So that's another way to skin it. But I mean, you hit the nail right on the head. If you have to depend on Goldman Sachs, Boeing, Ford, those kind of companies to deploy this, and they don't see direct motivation right away, like this gentleman said, it's going to be hard. So that, you first come up with the idea, you solidify it, you get some experience technically with it, and then you take it to the next level and see what happens. So, but really good comment, I think. Any other questions?
Thanks, Dino.
Thanks.